Okay, quiz 6, November 26th, Monday in class. As usual, everything's the same as we usually do. The good news is it's the last quiz. The bad news is the final exam comes after the last quiz. Okay. So, but anyway, I want to tell you some of the things that I'll be doing to help you get ready for the quiz. I know it's a short week. So as I mentioned, on Wednesday there is no in-class lecture for my section. So as a result, what I will do, so first of all, I will finish the material for quiz 6 today. All right. I will then, on Tuesday, tomorrow, we'll do the review of the topics on Tuesday. Okay. And then on Tuesday night, I will record the Wednesday lecture. That will be working through some additional practice problems for quiz 6. I will also record solutions for practice quiz 6. The practice quiz 6 is not yet publicly available, but Professor Iwasaki and I just discussed it. It will be posted this afternoon. Okay. Any questions about any of this? All right, and we also discussed which topics we will not cover on this quiz 6, but we may cover on the final exam. So, he will have class on Wednesday, and he will cover damped oscillations and resonance, which we'll talk about today. But those topics will not be on quiz 6. They will be sort of postponed for the final exam. Okay? Is that reasonable? Also not covered on quiz 6 is something we call the physical pendulum. This is what's called a simple pendulum, where you have a string and a mass. But a physical pendulum is more like something more complicated like this that we'll talk about today. Okay? Where you have some material consisting of the entire object that's swinging. Are there any questions? All right, some other things I want to mention that I have put up to help you get ready for quiz 6. Just 1 second. Let's take a look at some. Where is this? Let's go to practice problems. Okay, so these are new. These are gravitation. You can see that, right? Yeah. So these are gravitation problems. All right, these are all universal gravitation problems with solutions. Okay. The solutions are a separate file. And I've made a bunch of practice problems for oscillations. That's here, oscillations. Okay, a bunch of problems you can do here. In addition to that, I have uploaded a couple more, as though you don't have enough practice tests. You have a few more of them now. Because for some reason the quiz 6 material was not so heavily covered in some of the existing material, so I added a practice problems 2I and a practice problems there's a 3H, but I haven't uploaded it. Now that I'm looking at it here, I will upload it after class. I printed it out, but I forgot to upload it. Okay, so there's a lot of material here that you can use to get ready for quiz 6. And if you want to know which problems to do, I have made a list of quiz 6 things, gravitational problems. Okay, gravitational problems, all of them, oscillations problems, from 2G 12 to H 12, so it's just a list of problems you can go through. All right? Any questions about this? Everybody okay? All right, then let's get started with today's lecture. Okay, let's do a demo first. So this is a mass mass on a spring. However, if you have, usually we just draw one spring and it goes back and forth. But to be honest with you, if you just have one spring and you have a mass going back and forth, it's a little bit unstable. It doesn't really, that's a wiggle one. So it's a bit more stable if you have springs on both sides. Now, it may be a little bit confusing, but suppose I have, well, I don't have to suppose. You see here two springs. One with a spring constant K here, and spring constant K here. Does anybody know if I have two springs attached like this, and I stretch it like this, it will try to restore back to the equilibrium point? You know what the effective spring constant will be if each one is K? What will the spring constant be for the two springs together? K. The K? Yeah. Let's have another guess. Okay, let's think about it, right? So even though these springs look like they're stretched a bit, let's make it simple. Let's suppose the relaxed length of this spring is here. The relaxed length of the spring is to here. Okay. Now I'm going to stretch. I'm going to pull it to this side. So now this guy is pulling with this force. Okay. Fk is equal to minus kx like this. This guy is pushing in this direction. Fk with minus kx. They're both going in the same direction. Does that make sense? Okay. So with the same displacement, I'm getting twice the force. So what do you think the spring constant would be? Yes, two things. Right? So that's actually what's happening. When you have more than one spring doing the same thing in concert, then you add up the pace. So this is just an example of that. You can see what's going on here. When I let it go, you'll notice that it will accelerate in this direction. Okay? And then once it gets to the top, it will accelerate in the other direction. Right? And in the middle, there will be no acceleration. It will be just moving with constant velocity. Okay. So this is the mass. Questions about that? Good? So I should say in the middle, it just instantaneously has no acceleration. Because it's not truly constant velocity. A couple other things I want to mention. These are vertical springs. So they're a little different in that the true relaxed length of the spring is something like this, but because of gravity, it has a new equilibrium position like this. So by knowing how much it droops down from the relaxed length to position here, you can figure out what the spring constant is if you know the weight of this mass, right? That's pretty straightforward. Now, the thing I should mention, though, it doesn't matter that the equilibrium position is stretched a bit. It still behaves like a spring with a spring constant K around a new equilibrium position. So everything is just the same as for a horizontal spring, okay? A vertical spring. Does that make sense to everybody? All right. The other thing I want to mention are these two springs are kind of similar to each other. If I make one have a larger amplitude by stretching it more, and the other one not quite as much, notice that they still have the same period. They oscillate at the same rate. See that? So the amplitude, how high and how low they go, does not matter. It's really the period is related to the mass, the ratio of the spring constant over the mass, and it's not the same spring constant mass. Everybody got that? Okay. Now we're also going to talk about pendulum, a pendulum, and that's just when you have an object swing. This is what's called a simple pendulum. And the interesting thing is that the period of a pendulum is not affected by the mass of the ball. So this is a much heavier ball here. So I'm sort of taking the same. Well, okay, the problem is my hand lead, so it's a little stable. Let me try to get this back. Okay. Everybody see it's about the same period? Okay. Maybe you can't see. Even though this is about 5 times more massive. Now, if I change the length of the string, then the period will change. So notice if I'm making a much smaller string, thing is my hand is symmetric. Okay, let's deal with this. Okay, see it's much faster with this smaller string. Well, shorter string. Okay. Whereas when it's a longer string, it's much slower. So it's related to the string length, how fast it goes. Yeah, question? That's a great question. So the problem is it's hard. I was trying to get another hook so I can get another pendulum. But let's try to keep track. Okay, so kind of count in your mind. I'll do a big amplitude, bigger amplitude. It's like 1, 2, 3, 4. Okay, remember that. Now let's take a small amplitude. 1, 2, 3, 4. Doesn't seem to matter. Okay. In fact, this was the reason why they used pendula for grandfather clocks. You know, the old-fashioned clocks in the early, the medieval times. It's because the amplitude didn't matter. So even though it started getting smaller in amplitude, or the change in amplitude, it would still keep the same time. Now, the thing is, if you look at it, if you measure really carefully, there is some change. So that's why these clocks made of pendula are not that good. But to a good approximation, it doesn't matter. Okay. All right. Any questions?
All right. Let me just double check that my camera's working right. Okay.
Okay, so let's cover the new material. And I will sort of do a very quick review because it's been a few days since we talked about mass and spring. So let me just review all the things related to that. So we have our spring with a mass. And we have our x equals to 0 at the equilibrium point. Okay, and then we displace it, we stretch it maybe. And that displacement is x. And we have a spring constant. Okay, and a mass m. Okay, first thing about these oscillations for mass on a spring is the angular frequency. Remember, that's the guy that's in radians per second. And that's what we used to call angular speed, but because there's no circles, we'll just call it angular frequency. And that has the symbol of the omega, the small omega. And the formula is that's the spring constant divided by the mass. That's for spring, mass on a spring. Some other formulas is that we have the frequency is omega, sorry, F. Let me write it again. Frequency is F, small f, which is equal to omega divided by 2 pi. Okay, so that will be cycles per second, or inverse seconds. And so that will be 1 over 2 pi square root of k over m. Now, if we want the period, the time for one cycle, that's capital T.
and that's equal to 1 over the frequency, or 2 pi divided, I'm just writing all possible formulas you could imagine using. 2 pi divided by omega, and so that will be everything goes upside down. So you have 2 pi square root of m over k. Okay, any questions about this? Now, if I want to write the position of the mass as a function of time, then x as a function of t, I can write it as A. A is what's called the amplitude, cosine omega t plus phi. Okay, A is the amplitude. It's the maximum possible value the way this oscillation can have. Now, v of t, this is the velocity. If you want to put a little x here, you can, maybe I'll do that. The velocity, that's just going to be, let me see if I can make that clearer. That's going to be the time derivative of the position. And if I take the time derivative of this, the cosine becomes minus sine, and then the omega, because it multiplies t, it comes out in front, so I get omega times A times the sine of omega t plus phi. Okay. Can everybody do this? I know some of you are taking Calculus 1 at this point. If you're somebody in Calculus 1 and you follow this, raise your hand. Okay. All right, so enough of you raise your hand then. I think it's okay. Does anybody have any questions on this? Yeah.
How do you solve
For phi? To be honest with you, I'm not covering that too much. You have some of this in your homework. But the point is that the initial conditions determine what phi is. So if we just simply displace it from one point here and release it from rest, then phi will be 0, because it starts from the peak. It starts from the largest possible value of x. Okay. And cosine starts from 1. Right? But if it's something else, then what you have to do is you have to solve for, the basic point is, typically you're told something about how it starts. You're told the initial position and the initial velocity. Okay. And now you have here this formula for the initial position for t equals to 0, and here's the formula for the velocity when you set t equals to 0. So what you do is you'd say, okay, at t equals to 0, I have the initial position as a cosine phi, and the initial velocity will be minus omega times a times sine of phi. Okay, and then you can solve for phi. I'm not emphasizing it that much here. Okay, now if I want to get the acceleration, then I need to take the derivative of the velocity. So if I take the derivative of sine, I get a cosine, but I get another omega because of doing the chain rule, okay, because there's omega times phi. So I would end up getting minus omega squared a cosine omega t plus phi. Okay. Any questions about this? Everybody good with that? By the way, while we're talking about this, I just remembered I wanted to tell you that the equation sheet, the actual equation sheet, well, both things actually. Let me just pull this up. Practice quizzes. Oops, what happened here? Okay, so this is the real formula sheet for quiz 6. And you'll see these things are nicely written out for you, so you don't have to memorize these. Oops, what's going on with this? Okay, it's not getting bigger for me. I don't know why. Okay, there it goes. So these are all written out here. You don't have to memorize these. Does this make you happy? Okay. So I'm just showing you the derivations of these things, but they're all here. By the way, I've also put in a, let me show you. I've also put in with the reviews. All right, by the way, the notes for the review tomorrow are already up there. Here's the comprehensive equation sheet. Why is this so huge? I don't know what to do with this. Let's see. Okay, so this is the comprehensive equation sheet. For quiz 6, I have a lot of stuff. Here's for gravity, force, potential energy, orbit. Okay, and then for oscillations here, all this stuff. Okay. Let's get back to the lecture then. So I just was showing you, you don't have to memorize these things. Okay, but then what we had was we had a formula for the kinetic energy. And we had K was 1/2 mv squared. Okay. And we had that the potential energy for the spring is 1/2 kx squared. And I'm not going to go through the details again, but then you find that the mechanical energy is the sum of k plus u. And that ends up being just a constant 1/2 k a squared. It's constant in time. Okay. So if you know what the total energy is, you know 1/2 k a squared. Any questions about that? That's just a very simple review. Oh, I skipped the derivation because we did that last time. But what you have to go through these steps. You have to go. I'm sorry. This I believe is also there. Let's just take a look. Apparently not. I don't see it now. Yeah, it's not there. Okay. But the way you derive that is you just go through the steps. Okay, I put it in my notes. You get formulas for. Here, you can't see that because this is in the way. Okay, so you have 1/2 mv squared. You plug in the formula for v. You get some ugly thing like this. We did this last time, so I'm not going to do it again. And you put in the formula for 1/2 kx squared, potential energy. You get some ugly formula like that. And then you say omega squared is equal to k over m. And they both start looking very similar to each other. You add them together, and the sine squared plus cosine squared equals 1. Okay. Yeah, that's not in your equation sheet. It's kind of a useful formula. Any questions about that? So the very simple special case is when phi is equal to 0. The phase, this is what's called the phase angle. And this guy is equal to 0 when released from rest. That's very often the initial case, or the initial condition we'll use. When you just release something from rest, that's how it will go. Okay, any questions about that? All right. The next thing I want to talk about is what's called a physical pendulum. And this is the more general case. We'll talk about the simple pendulum in a moment. A physical pendulum is sort of like, as I was showing you here, suppose I have a pivot on this meter stick, and I want to know how fast this thing is oscillating. One of the things I would need to know is the moment of inertia of this meter stick around this pivot, this rotation point. Other thing I need to know is the distance from the center of mass to the pivot point, and I would need to know the mass of this object. Okay? So those are the key ingredients. So this is a general pendulum. So let me even draw it to look like a meter stick, a little fat stick like that. So we have a pivot, and this is the rotation point, rotation axis. Okay, and let's say here is the center of mass. And let's say the distance between the center of mass and the pivot is L. So notice it's not the full length of the stick, but it's the length to the center of mass. Your equation sheet, they actually use R for this, but we'll just call it L. And then we have some weight mg. So as usual, the weight of the object can be imagined as attached to the center of mass of this body. The weight is going straight down from the center of mass. And so capital M, so we let M be equal to the mass. I is the moment of inertia about this pivot. And then L is the distance from the pivot to the center of mass. Okay. Questions so far? All right. Now, I started writing my notes thinking I was going to, last night, thinking I was going to derive this all, but I remember doing this in the previous class, and students didn't follow it very well. So I'm going to skip some of the steps in the derivation of the physical pendulum and just tell you the answer. Okay. The angular frequency for this oscillation, remember that's the one that's called omega. It's radians per second. Radians per second is the unit. And that comes out to the square root of m, capital M, the mass, times small g, times the length from the pivot to the center of mass, divided by the moment of inertia, all inside here. So notice it depends on gravity. G is 9.8, usually 9.80 meters per second squared. Okay. And this will come out to have units of inverse seconds. Radians is not really a unit, so it's the same as radians per second. Now, so then the frequency, we can take all these different formulas of frequencies, omega over 2 pi, and so it's 1 divided by the square root of mg L over I. And we can also say the period. It's 1 over f, so that's 2 pi over omega, all these different ways of writing it. So that's 2 pi square root of I over ml, mg L. Okay. All right, so let me just say a couple things that maybe, well, since I didn't do the derivation, but the way you derive it, I'll just give you a sense of how it's derived. If you swing this object or you displace it by some angle, then there's going to be a force that's acting on the center of this
here, and that's going to make a torque. It's trying to pull it back down to the torque action here. Okay? So you can calculate what the torque is. The way you can calculate the torque, you can calculate R perpendicular, take the line through the force, and then you figure out that's the distance R perpendicular here. So if this angle is theta, like this angle here is theta. I'm sure you're following all my hand waving. Okay, alright, and then you can get this length here and the thing L times sine of theta. So then you can, okay, and then you can calculate the torque, and then you see that the torque is proportional to sine of theta, and then you say when theta is small in radians, that sine of theta is approximately equal to theta. You see, it kind of takes a long time to drive this. And then you say, okay, then torque, you use Newton's second law for rotation, that the torque then is equal to the moment of inertia times alpha. Hopefully you remember that one, right? Torque is equal to I alpha. It's like F equals ma with rotations. Tau is equal to I alpha. Okay? So now you have torque is proportional to theta, and then you have the torque is equal to I times alpha. The alpha is the acceleration, which is the time derivative of the time derivative of the angle. So then you get an equation that looks a lot like the equation we end up getting for the mass on the spring. That there's a relationship between the double derivative of the angle and the angle. And the formula ends up being the double derivative of the angle is equal to this guy here, this omega squared, mgl with a minus sign over I times theta, right? So you're probably glad that I didn't go through that derivation. Okay, but anyways, that's how you get this formula. Any questions about this though? I should mention this formula is not on your quiz 6. This was considered beyond quiz 6 material. But the simplification of this is what we'll be covering in quiz 6, which is what's called a simple pendulum. Simple pendulum. So the simple pendulum is a special case when we have a point mass attached to a massless string. Okay, so we just have mass on a string. This is the pivot now, which is just where the string is tied to something stationary. And then we have, this is the length of the string, is L. And so now we have some mass, so the force of gravity goes down like this. Okay, and it just swings back and forth again. All right? Well, let's just consider this case. In this case, the moment of inertia, right? Remember the formula for the moment of inertia for a point. If it's a distance L from the rotation point, it's going to be L times the distance squared. So the moment of inertia will be mL squared. And so what we're going to do is plug it into this formula we had before, mgL over I. Okay? So in this case, we have omega, the angular frequency, is equal to mg, okay, thank you, mgL over I. But I'm going to plug in the formula, it's mL squared, where it's going to get a bit simpler in just a moment, mL squared. And the m's go away, one of the l's go away, and I get the square root of g over L. So, for a simple pendulum, it's actually a simple formula. It's just the square root of small g over L. Notice that the mass does not play a role. That's why having this wood ball or having this metal ball didn't make any difference. So just g over L. If you take L to be smaller, the frequency will increase, and that's what we saw with the
smaller string, it was faster, the oscillations. Okay. All right, so now if we have omega is the angular frequency, this is the angular frequency. Let's do this once more so that you get familiar to all of these with all of the different things. So the frequency is omega over 2 pi, and so that's equal to 1 over 2 pi square root of g over L. And then we have the period, t is 1 over f, which is 2 pi over omega, and that comes out to 2 pi square root of L over G. Okay, any questions about that? Okay. Now, the remaining material I want to cover is the stuff that's not on quiz 6, but could appear on the file, so let me cover it. And this is concerning damped oscillations. So these oscillations, you'll notice, they don't keep going forever. In fact, you notice it has stopped. So eventually, this amplitude doesn't remain the same. It starts decreasing. You can see it right now. It's getting smaller and smaller. This is what's called a damped oscillation because there's some friction involved. And so we'll talk a little bit about how this works. Okay, so we'll talk about damped oscillations. And we're going to specialize to the case for the mass on a spring. And the point is that if we have a mass m, okay, and it's moving with some velocity v like this, then we have friction that opposes, and we have some drag force. Oops, I misspelled drag. Like this. And so in principle, it's proportional to the velocity. It is minus v, some constant, times the velocity vector. So when we have this drag force, I'm just going to tell you the answers because to solve this requires even more complicated differential equations that we've been skipping throughout this discussion. Okay. Instead of a simple oscillation, which we have been talking about, something like x of t is equal to a cosine omega t plus phi. Okay. We instead get a damped oscillation, which looks like the following. We get a damped oscillation where x of t is equal to a, and there's an e to the minus bt over 2m. Okay, mass m. The mass is equal to m. And b is this drag coefficient. And then the rest is the same, cosine omega tau t plus phi. So it's this extra term here that is all the difference. And what it does is, instead of having your nice sine function that goes like this, you get something that has an envelope that peters out like this. You get this behavior. Okay? And so this is x of t, and this is t. And this envelope here, this is what sometimes, well, your book calls it x maximum. That's the maximum it can get. It doesn't exceed this envelope. And it's going to be a e to the minus bt over 2m. So it has this exponential behavior. Does it make sense what I'm talking about? Instead of just oscillating like this forever and ever and ever, it has this ceiling and this floor, and the ceiling and the floor are squished to zero eventually with an exponential behavior. That's the exponential behavior here. It damps that away. Yeah, question?
So, will the period is still right?
Yeah, it will still oscillate just like a normal. Okay. Now, if we're talking about, so all this stuff is not on quiz 6, but I'm just trying to give you the information. Now, remember the mechanical energy we just discussed is E mechanical is K plus U, and it ends up being 1/2 small k A squared. So this capital K is for kinetic energy, this small k is for the spring constant. Okay, but we find here that the amplitude is not really constant. It starts to decay like this on this. For these damped oscillations, they're getting smaller. So as a result, the mechanical energy starts to decrease. So for the damped oscillations, we get that E mechanical is equal to 1/2 k x maximum squared, that envelope function, and that comes out to 1/2 k A squared, and then I have to square, remember this is x max here, so I have to square that A squared, and then if I square this guy, I get minus b over t m without the 2 because I square it. And your book likes to write this as mechanical energy as a function of time is equal to some initial energy e to the minus t over tau. I'm writing it this way because you have because that's the way your book writes it, basically. And so then if I write 1 over tau like this, then it's equal to tau is equal to m over b. And this is what's called the time constant. It's an estimate of how long the oscillation lives. If you wait a time much larger than this time constant, then essentially the thing has died away and you can't see the oscillation anymore. Okay. Questions about this? Yeah.
So that tau has nothing to do with any sort of torque?
Oh, no. See, yeah, so it has to do with the fact that we're lazy and we ran out of Greek letters. Okay? The last thing I want to mention, before I have you click in so you get a clicker attendance, the last thing I want to mention is driven oscillations. That's when you actually have an external force. External force drives the oscillations at some frequency f. Okay? So in other words, instead of letting this do it by itself, you are saying, I'm forcing this to do this. You know, you can imagine having an earthquake where it's actually made to oscillate at some frequency. Okay? And the point I want to make is that there's also something called, so let's say f is the frequency of the driving oscillation. And let's say f0 is the frequency of the natural oscillation when left alone. This is the formulas we've been writing down. We said omega is square root of k over m. And so the natural frequency for a mass on a spring would be 1 over 2 pi square root of k over m. That's my f0. And the point I want to make here is that the amplitude when f is equal to f0, this is called resonance. And this is when the driven oscillation has maximum amplitude. Okay, if you want an example of this, it's how many of you have ever pushed somebody on a swing? Okay, so, you know, a little kid, brother, kid, sister, right? You push on a swing. And there's a natural frequency for this. Well, here's a great example. So here's the pendulum. If I'm going in sync with the pendulum like this, notice how it keeps getting bigger, okay? But if I do just like, it doesn't really work, right? You're not really in sync. If you go too fast, it doesn't really add up. But if you're in sync with the natural frequency of the system, you get a very large amplitude. That's what's called resonance. If you drive it at the same frequency as the natural frequency. Okay, since you guys made the effort to come here, Thanksgiving week, let me just get out your clickers and click in for tennis credit for today. And when you have done that, I'll see you guys on